Hello, everyone. I hope you're having a great start to your day. My name is Shanan. I am an ML engineer at DagsHub, and I am super excited to be sharing this workshop with you guys today. So MLflow is a brilliant piece of open source software. It has a whopping 243 million downloads and 13,000 stars on GitHub. It is a very, very widely adopted open source tool for machine learning lifecycle management. And it has a host of features that includes live logging parameters, metrics, and artifacts. And in addition to that, it also provides a component called a model registry with deployment functionality. And that basically allows us to control or understand the entire life cycle of a given model, from figuring out what hyperparameters work best to setting it to a deployed state or a state at which it is basically retired in one fell swoop, right? And MLflow provides us with that interface. It is a very, very powerful tool, and it is something that I think is very, very crucial for anybody to have in their MLOps toolkit. So we integrated MLflow into DagsHub about 2 years ago, providing a zero configuration MLflow remote server with built-in access controls that supports MLflow's tracking, model registry, as well as deployment. So end to end. We've dived into its internals, handled many of its specifics, and we're very excited to share that knowledge that we have gained with the data science community. So that is you guys. So there are a couple of components that we will basically cover through this workshop series. The first is an intro to MLflow, where we talk about what MLflow fundamentally is and how it can help you manage your machine learning project. Second is experiment tracking, where we actually learn to live log parameters, metrics, and artifacts as part of machine learning experiments. And then we have the model registry, which allows us to log and manage machine learning models with MLflow. And finally, model deployment, wherein we take these models that we have carefully curated, trained, and managed, and deploy it using AWS. So for today's session, we will be covering the first two out of the four topics that or the four modules that we have basically designed. And we will use DagsHub's integration with MLflow just to speed things up. You would log experiments to a remote server using three very, very simple commands. So for that, if you would like to follow along through our workshop, please feel free to sign up to DagsHub. There are a couple of socials at the bottom as well, along with an MLflow's documentation or MLflow's website, which has a lot of handy documentation as well. So I'll give everyone maybe a solid 30 seconds, I'd say. Yeah, we can proceed. If there are any questions at this stage, I would love to take them now. In the meantime, we have a couple of memes over here to keep you uh excited or interested. But all right, it's 7:08. I guess we can continue. Was that 30 seconds? I'm not a very good, I wasn't counting very diligently, but anyways. So let's start off by talking about what we are going to learn about today. So first off, why do we need MLflow? What is MLflow? MLflow's tracking functionality, runs. So within that, we will talk about runs and experiments, why they are important, how we can log runs and experiments, and how and where are these runs and experiments recorded. So this is a bit of the MLflow theory. Finally, we will go and have a hands-on experience with MLflow, where we will take a project that doesn't have MLflow and integrate it to our suite. And that way we will know how exactly you could go about setting it up for one of your projects. So why do we need MLflow, right? We have a couple of memes here that talks a lot about data cleaning and data engineering, feature engineering, what you will. And the truth is that that is the fundamentally, that is a big part of what we as developers have to do for a custom machine, for a custom solution, because frameworks like TensorFlow and PyTorch automate the actual machine learning process for us. And setting up and creating a model is as easy as defining what layers we want, what type of layers we want, and then the optimizer learning rate, what you will, and it does all of the training part for us. The data is something that is very unique to our specific problem, which is why we have to be, which is why we have to manually involve ourselves with it and ensure that it is in a format that the very particular machine learning models can use to efficiently learn information about the specific challenge, and then hopefully the predictions make some sense. So the effort and time that is spent in figuring out exactly what combination of data cleaning or hyperparameters that are relevant to the project that make it work in an optimal fashion is very, very easily underestimated, right? Especially when you work with notebooks, you find yourself undoing and redoing a lot of times to find that perfect set of hyperparameters that gave you a really fantastic performance. And you basically generally, or at least usually, have to run a lot of experiments until you finally figure out that one awesome set of hyperparameters that works, right? And it's kind of funny because we describe machine learning as tuning millions and millions of dials, but when we have to tune these 4 or 5 manually, it becomes such a massive hassle. And one of the ways that one of my colleagues figured out to solve the problem was using Notion. It's a brilliant tool for note taking. And the way she did it was she set up experiment details, then the type of the data set, basically a general metadata about the experiment, and the log file that she took out of Slurm. And she used this as her interface to figure out which models perform very, very well. However, while Notion is a brilliant note-taking tool, logging experiments are a whole different beast, and they have their specificities that generally are not very, very easily, I would say, used or exploited by Notion, right? And MLflow does exactly that. It is an open source tool to manage the machine learning lifecycle. It supports the live logging of parameters, metrics, metadata, and artifacts, right? That are outputted when running a machine learning experiment. To manage the post-training stage, it has a model registry with the deployment functionality to serve the model that you have created. So it was created in order to reduce the complexity in monitoring experiments, to ease the reproducibility of results, which is especially important for a field like for anything that is within machine learning, because everything here is probabilistic, and machine learning models are so often considered black box, right? So we need as much of reliability as we can extract from these, which is what makes reproducibility so important within machine learning. And this tool does extremely well to cater to that requirement. Finally, it caters the need of a standardized mechanism to register and deploy models to production. So it was introduced in June 2018 to offer an open interface. This means that it is platform agnostic. You can use it for PyTorch, you can use it for TensorFlow, you can use it for fast AI, or any new fantastic platform that comes up in the upcoming recent future. It is also open source. So a lot of companies like Microsoft, RStudio, Facebook, etc., you could read through the list, have contributed to MLflow in order to extend its functionality. And it's a simple consequence of open source learning. You would see with models like Llama as well, they outperform a lot of proprietary software, simply because it's a lot of people or the entire community working together to build one fantastic product. And initially, a lot of these companies developed their own internal tooling to perform the same thing. And creating one open source software in MLflow allowed users, or allowed companies more realistically, to not rely on their own internal tooling and basically build in a more united fashion, as a result of which the resultant platform is fantastic. There is a reference brought to the statistics for all of the organizations that have contributed to MLflow, and you should check it out in the link below. So MLflow components, we've covered this, so I would be, I'll be kind of brief. The first one is MLflow tracking, which is what we've spoken about, where you can log parameters, metrics, as well as artifacts. The second is MLflow projects, where you package and reuse given data science code, so it works towards a reproducibility. The MLflow registry, which manages the lifespan of a machine learning model. So taking a model from training stage where it is experimental to deployment, and after deployment, once it is retired. The life cycle management is what the registry works to control. And MLflow models that allows us to package and deploy machine learning models with very, very little of a code overhead. So it dockerizes models and deploys them in a very efficient fashion. So that is a very, very fantastic tool that allows us to take it from a stage where we have the set of parameters that work well to something that can be deployed at scale very, very quickly. So let's start with talking about the MLflow's tracking functionality, right? And the first step to this is understanding runs and experiments. These are two units within MLflow and are used fairly extensively. The experiment unit in MLflow can be considered a project or an approach. So if you have a given architecture that you're pretty happy with and you want to perform some hyperparameter tuning on it, your experiment could be hyperparameter tuning. And within that experiment, you have a set of runs that basically refers to a single execution of the code. So if you have, say, 50 set of hyperparameters that you want to figure out which one works best, you would run all of those 50 runs with those 50 set of hyperparameters, and then within that experiment, compare each of the runs and figure out which run works best and use those hyperparameters in your final model. So that is the way that MLflow has envisioned the split, and it works very well in practice as well. So one important thing to remember is that more than one run might be associated with a single experiment, but not the other way around. So a single experiment cannot have, more than one run might be associated to a single experiment, but there cannot be one run that is associated with multiple experiments. Each run is an execution of your data science code, and it records the following set of parameters. The first one is the source of execution. So it contains the hash of the commit. If the code was pushed to any Git server, GitHub is one example of it, as well as the original line of code that was utilized for the run. So if you say run Python -m and then source.model.train, it will record that as well. So you know what command triggered the actual run itself. And the commit hash allows us to also find out which set of code, so which state of the repository was where the code was actually run. So that speaks towards the reproducibility aspect of the code. So there is that. Second, we have artifacts. These are the output files that are recorded during a run. So after a run, if you have an evaluation stage where you record a couple of sample images and predictions, or any feature data and predictions, it will record that. It also records, obviously, the model itself, because that is the critical thing that we want to get at the end of our data science training run. Then it also records parameters that are stored in a key value format. Parameters are metadata about the model. So maybe what kind of optimizer you were using. It could also include a set of hyperparameters. Basically, any information that doesn't change through the extent of your run, but is relevant to that specific run itself. Finally, you have metrics such as root mean squared error or ROC-AUC that are recorded in a run. Metrics are different because these vary within each step of the training sequence. So every single batch will generate its own error. Every single epoch has its own unified error, and all of that will have to be logged. So since that changes through within the run itself, that is classified as a metric. So that's the basic idea about runs and experiments. If there are any questions, now would be a fantastic time to ask. and Neil could hopefully help me out with any if they are there in the chat. And if not, I can go to discussing about.
So, can you see the chat, or should I read it for you?
Read it, please. I can. Give me
Okay,
a second.
sure. So we have a question from Matt. Matt is asking, for a run, what about data slash version? Is that logging somehow?
For a run about data state. Oh yeah. So the data itself is will only be logged if you are logging your data with Git. A lot of times that's not something that is that's possible to do. So DagsHub integrates DVC, which is data version control, and that allows you to store state information about your given data set. And that data, the hash for the state of the data is included within the Git repository with a pointer file, similar to how Git LFS works. So as a result, if you are using DVC to track your data and MLflow to log the commit that is for a specific run, your data states and versions are also tracked. But by default, if your data is not versioned, then it is not possible for MLflow to record it, because it only focuses on the Git's commit hash, and DVC integrates very well with Git, which is why that works.
I would just add one small thing about what Jinan just said. You can also use the log artifacts method from MLflow. It enables you to also log models and data sets. The visualization of the data set is not supported, at least if you're using vanilla MLflow, and also on DagsHub, in the sense where you can diff and view it. And this is why we would recommend using DVC for that.
In addition, one last thing that I could also add is the MLflow's artifact, when you set it to log an artifact like your data set, that it may be very, very large in size and does not change very much in between versions. It logs the entire thing all over again. So in 10 runs, if you have 10 gigabytes worth of a data set, you would basically be logging 100 gigabytes worth of data to your MLflow server. So data version control would not have that. It would be a lot more efficient because it would only log the updates in the changes and not the entire data set itself. It's fine. Artifacts works well for things like models itself, or outputs from the training run, whose sizes are not that much, and you would not directly compare the difference anyways. But for data sets itself, it's not the best option.
Okay, so we'll take another one more question, but then we need to get going. So also, Eugene, and be mindful the times with the answer. Are metrics predefined, or can we also provide custom metrics?
Both. So for MLflow has this awesome auto log functionality that we will be using today, where it automatically logs a series of metrics based on the framework that you have. So if the framework supported it, it will log it for you. In addition, you can also define metrics that you want to track by yourself, but that requires manual intervention. So you would have to edit the train step. But that said, it's super easy and intuitive to do. So it does not take very long.
Cool. So I think it's safe to move forward, and we'll take other questions at the end of the session, and also be here to reply on the chat.
Awesome. Thank you, Neil. Okay, so let's talk about how and where runs are recorded. So these runs, as we do quickly just recap, the runs and experiments are the two units of the MLflow, are two units of MLflow, and the experiment is the approach, run is the specific execution of the code. So how and where are these runs logged or recorded, right? There are a couple of ways for this, or a couple of methods that you could use to log these runs. And first, there are a couple of scenarios. So we will just basically walk through those. The first scenario is MLflow on localhost. It is a good first time technique to get started. It is the default way MLflow records runs if you do not do any setup beforehand. It basically creates an ML runs directory in the same directory as you perform your run. So the command that imports MLflow and uses the functionality, of course. then it logs all of the data in this format where we have ML runs 0, that is the name of the experiment, and within the experiment there are all of the runs and all of the data for the runs itself. There are a couple of limitations to this approach. It is not very collaborative because experiments cannot be shared with a team. And in order to look at the UI of the of the runs, right? Because it's just a lot of data, and you wouldn't want to read all of that data just as a text file. You can use the MLflow UI command through their CLI, and that would set up a UI for you, and you could view the comparisons between two different runs, and as many runs as you want, perform searches using SQL and all of that fun stuff. So this leads to the features of the UI itself. It has experiment-based run listing and comparison. So you can also compare runs between different experiments if you need that functionality. You can search for runs by parameter or metric values. You can visualize the runs itself. So in the loss function through epochs, you can visualize that and compare that between runs. You can also export the run results to a CSV if you want to perform some additional analysis on your runs. The second scenario is quite similar with the first one, where instead of logging it to your local file system, it logs it to an SQLite server. So it is a little bit more efficient in how it manages the data. Searches are a lot quicker because it uses an SQLite server, and SQLite commands are used when we perform filters or searches within the MLflow UI. And it's generally a step up over the general file system approach. The third scenario is once again similar to the first one, but instead of setting or directly logging through the file system, it is proxied through a server where you type MLflow server through your CLI. It would create a server for you, and you would log experiments to the server using HTTP requests instead of just directly writing data to files. The next scenario is MLflow with a remote tracking server, backend, as well as artifact stores. And here's where we really step up the ante, right? It is a very good and efficient and a scalable solution that you can use. And this diagram is really helpful to that. So there are a couple of components. There is the tracking server, the backend store, the artifact store, and all of them may be located on different hosts in distributed architecture. So they do not need to, reside in the same location. The MLflow client communicates with each of the different components, the remote host, as well as the artifact server, and deposits the data accordingly. So artifacts are deposited using AWS's Boto client, and the actual parameters itself are transmitted using HTTP requests, similar to the remote server. And all of that data is stored into a PostgreSQL server using SQL argument. And this is a fantastic solution, but with the caveat that it requires a lot of management on the user end, right? It's a lot of DevOps that it goes into this process. The next scenario is even more complicated than the last one, where it contains each of the same modules as the previous approach, right, up here. But instead of the local host sending data to two different remotes, so one would be the tracking server and the other would be the artifact server, the remote host contains an artifact proxy. So there is only one endpoint that your local host needs to focus or needs to really log or know beforehand. It sends not just the runs and all of the metrics and parameters, everything that is stored in the PostgreSQL server like last time, but also the artifacts itself through the artifact proxy or through general HTTP requests, and the artifact proxy deposits it into the remote S3 bucket. So that makes it a lot easier for an additional local host to be added to a cluster. And like the previous scenario, it requires a lot of additional configuration in order to work correctly. So the sixth scenario is MLflow X DagsHub, right? We have all of these above scenarios that we spoke about, and it can be a bit of a hassle, even for people that have a DevOps background. So to simplify the process, we decided to do all of the MLOps heavy lifting for you. We provide a free remote MLflow server with every repository. You can log experiments with MLflow to it. We can view its information, view any of the information that you logged using the experiments tab, and manage trained models from the fully fledged MLflow UI that is built into your DagsHub project. So you could look at the MLflow UI that you would see locally through the DagsHub remote. Whenever you create a repository on DagsHub, a remote MLflow server is automatically created and configured with that project. The repository's MLflow tracking server can be located at this URL. So DagsHub.com, that's the domain, your username, the repository name that you define, and .mlflow. And this basically directs to the MLflow remote, similar to how you would set up .git for your Git remote or .dvc for your DVC remote. So in this session today, we will be using the DagsHub integration with MLflow and log experiments to a remote server by running 3 simple commands. So that is our theory part out of the way, and we can start going hands-on. So to get started with that, I chose to use Eric Levinson's awesome project where he trains a neural network to classify images as containing either Mario or Wario. So I will let that load up very, very quickly. So it is a fantastic project, and I definitely recommend you check it out in its entirety when you have a moment. But to get started, I forked this project to create a base repository that we can use to basically work through the process of setting up an MLflow integration. And for that, please fork the repository from this URL, and this URL is also present inside the notebook if you are following along. And once you press the fork button, it should basically redirect you. You can choose the repository name. I'm happy with this, so I will keep it as is. And very quickly, it should give me a fork of the base repository. Now, very quickly, I can take a look at the experiments tab where I should have all of the MLflow UI basically, right? And it tells me that I do not have any experiments right now. That makes sense because this is a new MLflow server or just recently configured. If I want to take a look at the MLflow UI, I can also hit this remote tab, go to experiments, and press on this, press the go to MLflow UI button, and that takes me to the MLflow remote UI. And over here also, I can see that there are no experiments. Again, this makes perfect sense because we have just set up the repository and don't have or haven't logged any experiments to it. So to get started, you would require the DagsHub client repository. So I would just run that real quick, and you can enter all of the information that is relevant to your account. So here is my username, my email, as well as the repository name. Since I didn't change it, this basically stays exactly the same. Once these environment variables are logged, I will also log in to DagsHub using an OAuth token so that I do not have to enter my password. And as soon as I just press accept, it will log me in, and the previous cell basically registers as completed. So this variable currently contains my DagsHub token. Now, these are our priors basically sorted. To start off, we can clone the project. So we will set up Git very, very quickly and clone this project to our Colab environment. So right here, it shows us Mario versus Wario, and we cd into the environment as well. So into this repository. So our current Colab environment is right here. Next, we need to actually install MLflow. The way we install MLflow is similar to how we install the DagsHub client repository. We use pip. There are a couple of additional versions that we can use, but for now, we are just going to stick to the default MLflow version. And once that is set up, we can also look at the actual data pipeline that this project has, just so we get a little bit of a better idea about what this project even does. So we have this train stage right here, and this train stage takes a couple of inputs. It takes as input our data, and this data is tracked using TVC. So whenever we perform a run, the hash information for the run is also for the data is also stored. We have this config.py file that contains stuff about hyperparameters, as well as the training.py file that it looks like it is the actual driver for this code. And once the stage is executed, it will generate a model directory, which we are also tracking. And we can see that the command that we registered over here is Python 3 source/train.py. So that's the main driver for the stage. So we can just run that as well to see what is actually happening under the hood. And as that happens, I am very quickly going to open up the train.py file so we can walk through what is actually happening. We have a get datasets function, or a get datasets method, that is getting us dataset generators for training, validation, as well as test, and a get model function that sets up 3 convolutional layers, flattening a couple of dense layers, fully connected dense layers, and the final prediction layer with sigmoid activation, because this is a binary classification task. Okay, speaking of which, I also realized that I need to explore the data a little bit just so we have a better idea of what we are working with. We have within our data directory, we have, let's look at some training data. Let's leave this for later. So we have a couple of information, a couple of images of either Mario or Wario. And what this project does is it basically takes out these screenshots from the video game, and we have manually classified these as containing one of Mario or Wario. So as soon as I can open this, and maybe one image of Mario, we can see that this image right here contains Wario, and this image, as soon as it loads up, should contain Mario. And so it does right here. So we have these images that contain Mario and Wario, and we need to basically classify, or we want to classify whether it contains which character, right? And in this scenario, we are considering the fact that every image contains either Mario or Wario, and it doesn't contain neither of the two. So that is our task description. We have that is why we have the convolutional backbone with the fully connected layers and the binary classifying final dense layer. We're using binary cross entropy for loss and reporting accuracy as our metric. These are our hyperparameters, so the image size, the learning rate, as well as the number of epochs. We perform the training, some model evaluation, and then we finally save our generated model. So we can see that this run is just about completed now. So perfect. I am super happy with that. It set up the training run for 5 epochs. We can see that we get an accuracy of 58%, which is not amazing, but not awful either. On our test set, we get accuracy of 51%, so almost as good as flipping a coin. So we are 1.11% better than that. So I would take it. But that's our basic run, right? Our focus for today is to make sure that we can set up this training run reproducibly, and then maybe we can focus on how we can make this a bit better in a bit. Maybe the reason it's working poorly is because we have data corruption, and there is Mario right there in every single image, but we will never know. But anyways, that is our base training run setup, right? Now, if you want to figure out how we can log our experiments locally. To start with, this is the scenario 1 that we covered in our theoretical aspect. So the step 1 to it, of course, is importing MLflow itself. Once we do that, we can create an experiment and give this experiment a name. That name is completely our choice. So we can create this easy helper function where we define a function called getExperiment, and by ID. So we give it this name, and we attempt to get this experiment by the name. If this experiment does not exist by default, it will return none instead of an experiment object. And if it is none, we want to create it with that name. And then accordingly, we just return the experiment ID because it gives us the ID after the experiment is created as a return type. So we return the experiment ID. And in the event that we actually get an experiment object, so we just pick out the ID from there and we get the experiment ID using this function. So this is already something that is set up. So the get or create MLflow experiment.py file that is there right here. I will run this, and our experiment name in this case is Mario_Wario, and it should return the experiment ID for this specific experiment. If I refresh this, we see that there is an ML runs directory, and you can verify that this number matches this exactly, which is the experiment that just got created for our runs, whichever runs that we want to track. We don't have anything currently, but we will soon. So that's that. Next, we can allocate a specific run to our experiment. So we start runs in MLflow using the start run command within their Python API. And within that, we can specify a argument for the experiment ID. And in this case, it will basically log the run to the specific experiment that we set up. If we do not specify what ID to put, it will just set up a new experiment and create a single run within that. So information about logging. Okay, also one note, the code that follows this line needs to be indented with into this with block. And okay, information about logging. Once we have imported MLflow into our notebook or Py file, we can start manually logging any information that we want to log to our run once we set up this start run in our code. So we have parameters that we can log using mlflow.logparam within their Python API, where we provide a key value pair and it will log that parameter. So learning rate 0.001 10 to the power -3, something like that. The number of epochs, which would be 5. MLflow log params, if you want to log all of them simultaneously, we can do that using the log params functionality, where we just provide a dictionary that contains a set of key value pairs, and those are logged to the specific run. Then we can log a metric. So in this case, the test loss. We can also provide a keyword argument for step. So, oops, I guess editing over here was a bad idea. I can do it anyways. So I can provide a step keyword argument, and the step could be 1, 2, or basically any numeric value, and it will log that and graph it once our run itself is complete. And similar to how we could log multiple parameters using a dictionary, we can do the same for metrics, where we provide a dictionary. Again, we can provide a step as a keyword argument outside the dictionary, and it will set up those metrics for the specific step. Next, for log artifacts, once you have completed your training run and save your models to a specific directory. So if we quickly pull up our train.py file, we can see our the directory in which we are saving it, which is models_directory. So we can just set MLflow to log artifacts and give it this directory, and it will log that entire directory to the MLflow tracking server. Finally, you can also log any random bits of text that you think is relevant. So you would specify all of the text that you would want to write. So here you can have general information about the run and the file name within which you want to save it. So run_info.text. And that is where the information is, or the text itself is stored. So that's it. Let us set up our training run with MLflow. So to start with, I am going to scroll all the way up and import MLflow right here. And once that is set up, following the tutorial, we need to set up the start run. I am going to do that once after the model is initialized and we are actually beginning our training sequence. So with MLflow start run, and for the experiment ID, I am going to also import the get experiment ID function from the get or create MLflow experiment.py file. So I will do that as well very quickly. from or create MLflow experiment port get experiment ID, and here I will set up get experiment ID, and Mario underscore Vario is the one that we'll be using. So I will keep that consistent. Once that is set up, we can indent this to run within, to fall within this run itself. And as an example of just logging one thing, we can set up the parameter right here. MLflow.log parameter, and I will set the image size to 128. I wonder, okay, there we go, that's gone. So that is an example of logging a parameter. I'll also go ahead and log the artifact. So mlflow.log underscore artifact, and I will give it the models directory, and we can see that it will log that information as well. Finally, I will also log in a metric. So mlflow.log metric and set up test set loss and give it as input the test loss that I would want to log. So that done, or that said, we should have all of what we need to set up our individual logs, or like to log all of our information, right? Or whatever we wanted to initially log. So time to see the magic. Let's, attempted relevant import with no parent package. Oh, I need to set up source dot trail. Will this work? Okay. I am not familiar with this error. There's already a file system mounted. Oh, I don't need to run the install hooks command again. All right, there you go. So that is the training run, and hopefully, if everything goes or works fine, we should see information get populated into these ML runs experiment that we have set up. So within one of these folders, it will specify a run, and then accordingly, it will create all of the data within the run itself. So all of the information should be visible within the run under this experiment once our run completes. So let's give it a second. It completed training. Accuracy now is worse than rolling a dice, which is unfortunate. But here is our information. We have this run ID that we have, and there is a bunch of metadata that refers to the run name, the run ID, the experiment ID, all of that, the artifact URI, so the location where the artifacts are present. If you see the artifacts, it is basically copying the models directory that we have right here and just saving it into this specific run folder. So that is what it is doing under the hood, which is why if you were to log a data set under artifacts, that would basically create all of the information all over again, which would not be super duper efficient. So the structure in a more structured format, we have the experiment ID, the run hash, artifacts, the metadata, metrics, any metrics that we log. So in this case, we log the test set loss, so that information also is present right here, and parameters, tags, and metadata for the actual experiment itself and not the run is also present in the root folder of the experiment ID. So that is the general scenarios one file structure. Now, if you were to log experiments to a remote tracking server, to avoid the long process, we would basically just set up DagsHub's integration with MLflow. So the location, just to recap, is located at this address with your username and your repository in place of the defaults that we have set up over here. In order to set up DagsHub as a remote URI, all you have to do is set this command within the Python API, where you would specify your MLflow and where you would specify your MLflow remote. And you will also export your username as well as your password in order to ensure that your data is secure and people cannot randomly log unnecessary information or spam your MLflow remote server. So I'm going to do that very quickly. We can also set it up as an environment variable and then log it over here or just directly do it. It does not really matter. So I'm going to open up our get or create MLflow experiments Python file and set our tracking server through here, set tracking URI, and also I need to put OS real quick. OS.get env MLflow tracking URI. All right, that done. I will save it, and that is all of the changes that we have to make. So now, if I run this get or create experiment, we see that we get the experiment ID of 0. But in this case, it is not using the ML runs directory to get that 0 value. It is actually using our remote server from here in order to get it. So if I refresh this server, I should find the Mario_Wario experiment, which I see right here, that got set up when we use the Python API with a tracking URI set beforehand. So that is setting the URI. We can rerun this code to see all of the training logs, this time in our remote environment. So I am going to do just that. Now, this run should be identical to that of our previous one, except that in this case, instead of logging it to the local MLflow tracking server, it should load it to the remote MLflow server. I see a refresh button. I should have just pressed that. But now that I see it, we have this run within our experiment, and it shows us the status of it that it is unfinished. Here are the parameters that we logged as well as the metric itself. So that is this experiment that we have been able to successfully log using MLflow. But now we did mention that this process itself can get very, very tedious as well, right? Because you have a whole series of metrics that you want to track or a whole series of parameters that you want to track. And in the spirit of letting MLOps tools do the heavy lifting for us, we can log all of our information to a run with an autologger. And this is very, very, very useful as a tool because it automates the entire process of setting up what metrics we want to track. So it is supported for the following platforms: scikit-learn, TensorFlow, PyTorch, FastAI. All of the big ones are supported, which is fantastic. So in order to set up this integration, we need to get back into our train.py file. And before we begin our run, all we need to do is we need to set up MLflow or call mlflow.tensorflow.autolog, and that's about it. Once that's done, we can run our code once again, and very, very quickly, we should be able to see that reflected in our experiment section. And when we compare the two runs, you would see the sheer difference in the amount of information that we were able to capture with these first run and the second run. So we can already see these metrics over here that we did not log previously, mostly because I was feeling a little bit lazy. And here are a couple of parameters as well that are very relevant. So I will open this up very quickly. Here we can see that our entire experiment itself has completed running. And to go into light mode very, very quickly, we can see how our accuracy has evolved through each of the 5 epochs. Same for the loss, validation accuracy, as well as the validation loss. And ideally, we want to pick a model that it has or gives us the least validation loss. So Epoch 5 is looking really good at this stage. And it does seem that we are reducing. So this model does have some potential after all. Maybe we just need to train it a little bit more or perform some hyperparameter tuning. Either way, this is our experiment logging. We can see all of the parameters that we were able to log. Like before, it's a lot more than that of the previous one, and the metrics as well. We can also compare to we can also compare to MLflow runs, and I will showcase that in half a second as soon as these requests can load up. But it's not going to be very, very helpful simply because of the fact that we don't have a lot of parameter or a lot of data in our initial run. So if this shows us a cross comparison of all of the information that we have, we can see the image size is the same because that is what we had defined. We can see that we are also logging the test set loss, and they are both similar because the runs are nearly identical. And it compares test set loss as a bar chart simply because that is the only metric that we have logged, and it logs the last value basically. And we can see that a lyrical dog 23 is marginally better than masked deer 290. So make of that what you will. But that's basically all of the changes that we needed to do. And to finally just save the project, you can just run git commit, and any commit message of your choice. I chose added MLflow logging and push this to the remote. And just like that, you should see those changes reflected. And the commit hash for your git code should also be reflected in any of the experiments that you do from there. So very quickly, we can see the added MLflow logging message that this come up. And that concludes everything that I had to talk about today. You have successfully, hopefully, if you were able to follow along or enjoy this session, be able to integrate MLflow in any of your projects that you have currently been using. If there are any questions at this time, I would love to take them. Yeah, thank you very much.
Thank you, Jinan. So the stage is actually now yours, and you had a lot of very good questions on the chat. So before I'm going to recap on the question we had on the chat, so people back home that see the recording can also enrich their knowledge from it, I would want to open the stage for everyone who is still here. So feel free to open your mic or ask it on the chat. The stage is really yours. We wanted to be more of a conversation style rather than just Jinan talking to dark boxes on the screen. So really feel free to open your mic and just tell your name and the question you have.
Hi, Camille here from Dallas. That was a fantastic talk. I may have missed it, but what's the pattern for handling multiple projects? So let's say, in my question I asked, we have this Mario versus Wario. Let's say I have another project where I'm classifying apples versus oranges, and then a third project where I'm doing regression. And I split my time between them just like any other data scientist. But I want to log all my experiments to the appropriate, appropriate MLflow instance, or so what's the pattern there? Thank you.
So I'll take it, Jinan. Stealing your thunder, sorry. So I'll start by giving the answer that as now I understand is not directly answering or not fully answering what you asked. So first and foremost, the way that we are configuring the MLflow remote server is that every project on DagsHub has its designated remote server. So if you have a project for classifying Marses versus Wario images and another one for bananas versus apples, then each one will have its own designated remote MLflow server. So this is the way that you separate it. And this also means that only if you have access to that repo, you'll be able to log that experiment to the MLflow server. And what you're getting out of it is team-based access out of the box. And this is something that if you're not using the integration, you'll have to set up, and As a DevOps personnel, it's a huge pain. On the setup side, and this is a workflow question, I would say, or best practice, what we recommend is to use environment variables for your authentication. So setting up your DagsHub username and token as environment variable in your machine, because this is going to provide you the access to the writing access to those projects. However, setting up the tracking URI that you want to log to should be only in the code files that you're using, that you're running in the project, meaning you now transition between different projects, then you run it, you are reconfiguring the tracking URI in the runtime, and this will tell MLflow to log the experiment to that project, to project A and not project B. However, the authentication will be pre-configured as environment variables, and this way you don't need to change them or configure them every time that you're running the experiment. And also this way, you're not accidentally version them, let's say, with Git and pushing them to DagsHub and then making them public, because your token is secret and it's better that it will be stays private, I would say. Does it answer your question?
Yeah, that was great. I guess I didn't catch the part that there's a separate MLflow instance per project. I like that.
Thanks.
Thank you.
Thank you, Victor, for joining. Bye-bye. I'm going to start by reading questions. If people wants to ask questions, then feel free to open your mic. Grant, so if someone wants to respectfully comment on the validation ACC to show the model is not learning at all, how would you do that at that point? So currently, commenting, basically DagsHub enables you to comment on pretty much all of the files except for experiments. And in this case, what we recommend is we also enable commenting on notebook cells. So we see data as king and treating it as first-class citizen, but also Jupyter notebooks, because we know this is a very helpful tool for to develop machine learning. So what you can do is visualize those graphs in your notebook as the results of the experiment, and then have people comment on that. However, we are now taking it as a request, as a feature request, to be able to also comment on experiment and specifically on the results of the experiments. So thank you for the input. So we will share the recording. So there was a question here: if you're gonna share the recording, then we're gonna share the recording hopefully in the upcoming week. Matt, issues referencing the experiment should work too. What do you mean by referencing the experiments? If you want to share the experiments with people on the team?
Hi, can you hear me?
Yeah.
I was just responding to Garrett's question about the comments. If you just open an issue and reference the experiments and the accuracy, that should be an acceptable approach, I think.
Yeah. And it's also can be part of the pull request. So if you're opening a pull request with all the different experiments, this is another way that you can communicate over the experiments. And it's important to know that each experiment on DagsHub has a unique URL. So this way you don't need to share, I don't know, a screenshot on Slack and move to third-party platforms to communicate. You can simply take that unique link, drop it on either a comment on a Git commit or in an issue on a pull request and communicate over it there. What else? Jinan. So another question that Grant had here. When you set up a remote logging scenario, does MLflow also log locally? So you have a record of your on your system. So do you recall if we're setting up the remote server and using the remote server for logging, does it also log it locally under the run directory?
No.
No?
If it is running, I can actually verify this very quickly because we have the environment, collab environment still there. But yes, whenever we set a remote server, it does not log any information locally. I just check the ML runs directory where the ML runs directory within the Colab notebook, and there is run 0 that only contains metadata. But if you look at the MLflow tracking server, run 0 or experiment Mario with run ID 0 had all of the metrics with the 2 runs. So when it's logging, it doesn't log to multiple places simultaneously. Not as yet, I think.
Awesome. And another question that was
I think,
recurring.
Garrett, I think you're muted.
Sorry, I clicked the wrong button there. Yeah, so if you were logging a critical file like a model and you wanted a copy of it, would you want to then log it to MLflow remote and then also write it for safety to a local system? Is that the idea?
Well, I feel like the safety is logging it to the remote, I would say.
Well, let's say that
this way,
I mean, you're putting it over a network. So let's say something failed there. And I mean, what I would do is write it locally for safety and then potentially log it remotely. Is it for artifacts? Is that something you'd have to manually do, or is there a setting within MLflow that you can sort of do both?
so I think, yeah.
I don't think there is a. I don't think that there is a setting.
It's an esoteric question. I was just curious. You can always write it locally. So.
Yeah.
Yes. So you can either dump it locally or use DVC to version it as well. So you can use DDA, but yeah, it also will mean that you're gonna rely on your network. Yeah, so it's a safety measurement that I to be honest, I never encountered that need, but it's a good one. So if there is a need, then we probably need to think how can we solve it. Yeah, I don't think there is currently a good out-of-the-box solution for logging it both locally and to the remote. We can check for methods if MLflow has any methods that supports it, but probably going to take it offline. And Garrett, I'd love to ping you if we're going to find something that is helpful. A recurring question that we had here was about how to tie, or how MLflow ties the code version to the MLflow run. So especially when you're using notebooks. So what's important to note here, that every time that you're gonna start a run with MLflow, what it's gonna do, it's gonna basically look in the directory that you're running the code from for the latest git commit, and it will tie that git commit to that run. So it's a pretty straightforward solution versioning wise. So it doesn't do much. It's just looking for the git commit and log it as a parameter to the run. And this means that if you want to, let's say you're running from your notebook, you are changing the code there, and then you're starting a new run. What you need to do is commit the notebook again to save it, and then start the run. You can do it easily if you want to use code or do it programmatically with DagsHub client, which currently supports also logging of Jupyter notebooks from within the notebook. So all you need to do is run one line of code, and it will commit the changes using Git and push it also to DagsHub. And this way, you'll be able to automatically also version your notebook and make sure that the code that you're running is logged and versioned with the run that you created. Let's see if there's any other questions. No. Cool. So I think with that, I want to thank everyone for joining us today. It was awesome. And I want to thank Jinan for giving a fantastic session. One of our best, definitely so far. We will share the recording in the upcoming few days, hopefully sooner than later. And I wish you all a great rest of the week. and good morning, afternoon, or night. So DAGs out.